Most people, when they first hear asteroid belt, picture something just past Mars, close enough to reach in a few months if you point a spacecraft in the right direction. Here is what that intuition misses. Dawn, one of the most fuel-efficient missions ever flown, took nearly 4 years just to reach Vesta. Psyche, launched toward a single metal-rich world in that same region, needs 6. Something in that math does not add up, and the gap between your assumption and those numbers is the entire subject of this video. By the time we finish, you will know exactly how long it takes to reach the rocks scattered between Mars and Jupiter, and you will understand why those times look the way they do. Because the real obstacle was never how far away the belt sits. It is what happens when you actually try to stop there. And once you see why arrival is harder than distance, we will also settle a myth. Hollywood has been selling for decades that this region is a chaotic field of tumbling debris. It is not. Let's start with where the belt actually is. The first problem is that the asteroid belt is not a point on a map. It is a region, and its distance from Earth depends entirely on where both worlds happen to be when you launch. Based on average distance from the Sun, the near edge of the belt sits somewhere between 1.2 and 2.2 astronomical units from Earth, roughly 180 to 329 million kilometers. That is the close scenario, Earth and the belt on the same side of the Sun. But orbits keep moving, and half the time the belt is on the opposite side of the solar system from us. From that position, the distance stretches to between 3.2 and 4.2 astronomical units, close to 630 million kilometers at its worst. At that range, the belt is effectively as far away as Jupiter. There is no single number for how far the asteroid belt is. There is a spread, and where you fall in that spread is decided the moment you choose a launch window. This is why no mission takes the long way. Every serious proposal assumes the closest possible alignment, because doing otherwise adds hundreds of millions of kilometers for no scientific benefit. But even the closest approach still demands a flight path shaped like the Hohmann transfer we have covered before. An elliptical route timed so the spacecraft and the belt arrive at the same point in space simultaneously. Aim for where the rocks are today, and by the time you arrive, they have moved on. Add gravity assists to borrow speed for free, and ion propulsion to sip fuel efficiently over years instead of months, and you have the basic toolkit. Distance sets the boundaries. Timing and propulsion decide everything that happens inside them. Now let's see what those tools actually produced. Here is the part that will surprise you. Reaching the asteroid belt has, historically, been fast. Extraordinarily fast. Pioneer 10 entered the belt on July 16, 1972, just 135 days after launch, on its way to a rendezvous with Jupiter. It became the first spacecraft to prove the region could even be crossed safely. Voyager 1 did it faster, arriving at the belt in 96 days. Voyager 2 launched 15 days after its twin and somehow arrived on the exact same date, a total transit of just 81 days. New Horizons, the fastest spacecraft ever launched, left Earth at roughly 58,500 kilometers an hour and reached the belt within months, close enough by June 2006 to fly past the small asteroid, APL, a mere 145 days after launch. Read those numbers again. 3 months. Under a year for the fastest crossings ever attempted. If reaching the belt were the whole challenge, this video would be over already. But every single one of those missions did the same thing on arrival: nothing. They flew straight through. Pioneer 10 kept going to Jupiter. The Voyagers kept going to the outer solar system. New Horizons kept going to Pluto. None of them slowed down because none of them carried the fuel to slow down, and none of them were built to. This is the distinction that changes everything. Crossing the belt at speed is a straightforward problem of pointing a spacecraft correctly and letting momentum do the work. Stopping inside it, matching orbits with a specific rock instead of blowing past the whole neighborhood, is an entirely different mission. In space, braking costs exactly as much propellant as accelerating did in the first place. Every kilogram of fuel needed to slow down has to be carried the entire distance first. Fast crossings prove the belt is reachable. What they do not prove is that it is easy to arrive. For that, we need to look at the missions that actually tried to stay. If one mission makes this entire argument concrete, it is Dawn. Launched September 27, 2007, Dawn was built to do something no spacecraft had ever done: orbit not one, but two different worlds in the asteroid belt. Its targets were Vesta and Ceres, the two largest bodies in the region, together accounting for roughly 45% of the belt's entire mass. Both had survived relatively intact since the earliest days of the solar system, yet their compositions turned out to be strikingly different, making them a natural experiment in how planets form and diverge. Reaching them the conventional way was never an option. Chemical engines would have required a prohibitive amount of fuel to slow down for one orbit insertion, let alone two. So Dawn flew on ion propulsion instead, 937 pounds of xenon gas, thrusting almost continuously for years, rather than burning in short, powerful bursts. In February 2009, it swung past Mars for a gravity assist, borrowing velocity for free and bending its trajectory toward the belt. Even with an efficient engine and a free boost from Mars, the numbers stayed brutal. Dawn did not reach Vesta until July 16, 2011, a transit of 3 years and 9 months. That is longer than Apollo took to reach the Moon and back several hundred times over. But the payoff justified the wait. Dawn became the first spacecraft ever to orbit a main belt object, spending 14 months there and returning more than 30,000 images. It confirmed Vesta has an iron-nickel core and identified it as the parent body of the most common meteorite type ever found on Earth. Then Dawn did something no spacecraft had done before or has done since. It left Vesta, and using that same patient ion engine, reached Ceres in March 2015, becoming the first spacecraft in history to orbit two separate celestial bodies. There, it found bright salt deposits inside Okator crater, evidence of brine still bubbling up from beneath the surface today. Dawn finally ran out of fuel to control its orientation in October 2018, 11 years after launch. Its lesson was simple and expensive to learn. Ion propulsion works. It is efficient, reliable, and precise. It is also unavoidably slow. Dawn proved orbiting was possible. The next generation of missions asked for something harder. Touch the surface, take a piece of it, and bring that piece home. OSIRIS-REx launched September 8, 2016, bound for a near-Earth asteroid called Bennu. The transit took just under 2 years, arriving in 2018, dramatically faster than Dawn's journey, because Bennu orbits far closer to Earth than the main belt itself. But the mission still spent nearly 2 additional years in careful survey before it dared touch the surface, because matching the rotation and gravity of a 500-meter rock precisely enough to grab a sample without crashing is its own kind of arrival problem. It succeeded, and on September 24, 2023, the spacecraft swung past Earth and dropped its sample capsule home. Renamed OSIRIS Apex, it is now on its way to a second target, the asteroid Apophis. Japan's Hayabusa 2 followed a similar philosophy, traveling to the asteroid Ryugu, deploying small rovers onto its surface, and returning physical samples to Earth, building directly on the lessons of the original Hayabusa mission a decade earlier. Then there is Psyche, currently in transit to a target unlike anything visited before, a metal-rich asteroid that may be the exposed core of an early planetesimal, a fragment of a planet that never finished forming. Its cruise will take roughly 6 years, arriving in 2029, longer than Dawn needed for one destination, let alone 2. And Lucy is attempting the most ambitious itinerary yet, a tour of 8 separate Trojan asteroids sharing Jupiter's orbit, a mission that will not conclude until 2033, more than a decade after launch. Every one of these missions confirms the same pattern. Getting to the neighborhood is the easy part. What consumes the years is matching speed, matching orbit, matching rotation, precisely enough to stop, to land, to grab, without simply becoming another fast flyby. Here is the truth this entire video has been building toward, and it deserves to be said plainly rather than softened. Distance was never the real obstacle. Stopping is. Accelerating in space is the easy part. Once a spacecraft is moving, it keeps moving, for free, indefinitely. Arriving slow enough to be captured by an asteroid's gravity, to orbit it, to land on it, to match its exact rotation, that is where the entire cost of a mission hides. Braking in space costs exactly as much propellant as accelerating did in the first place. And every kilogram of that braking fuel has to be lifted off Earth, carried across hundreds of millions of kilometers, and then burned against a spacecraft's own momentum. The required mass grows exponentially as you ask for more precision. This is why Dawn needed ion engines and a Mars flyby just to slow down enough for one orbit, let alone 2. It is also why the next generation of propulsion is measured in how well it brakes, not how fast it launches. Nuclear thermal propulsion, a reactor heating hydrogen instead of burning chemical fuel, could theoretically cut a Mars transit to around 90 days at closest approach, and scale to roughly 293 days for a trip to the belt. Nuclear electric propulsion promises similar gains further out. Both exist today only as prototypes, not as flight-certified hardware. Further out on the theoretical edge sit ideas like the EM drive, which some calculations suggest could reach the belt in roughly a month, and antimatter propulsion, estimated at 10 milligrams, to cut a Mars trip to 45 days. Neither has moved past the laboratory. One remains scientifically disputed. The other remains staggeringly expensive to produce in any usable quantity. None of these technologies change the fundamental rule. They only change how much it costs to break it. Until something moves from theory into an actual flight-ready engine, the pace of arrival will keep being set by exactly what it has always been set by: propellant, patience, and precision. There is one more assumption worth correcting before we close, because movies have sold it so effectively that most people accept it without question. The asteroid belt is not a chaotic field of tumbling rocks, close enough to dodge and collide with at every turn. The reality is closer to the opposite. The belt is staggeringly empty. Objects inside it are typically separated by hundreds of thousands of kilometers of open space. And the history of spaceflight backs this up precisely. 12 separate spacecraft have now crossed the asteroid belt: Pioneer 10 and 11, both Voyagers, Ulysses, Galileo, Near, Cassini, Stardust, New Horizons, Rosetta, and Dawn. Not one has ever collided with anything. Before Pioneer 10's crossing in 1972, engineers genuinely worried that debris density might destroy the spacecraft outright. That fear turned out to be almost entirely unfounded. Current estimates put the odds of a probe striking an asteroid at less than 1 in a billion. So the danger was never navigation. It was never dodging rocks in the dark. The entire challenge, from the very first crossing to Dawn's careful arrival at 2 separate worlds, was always about matching speed and orbit precisely enough to stop, not about surviving a field of debris that, in truth, barely exists at all. So here is where that leaves us. The asteroid belt was never far in the way that mattered. Pioneer 10 crossed it in 135 days. What took years was Dawn slowing down enough to orbit 2 separate worlds. And what takes Psyche 6 years is the same problem: precision, not proximity. That is the actual story of exploring this region. Not a graveyard of tumbling debris, but a quiet, spacious frontier we have crossed a dozen times without incident, and only recently learned how to stop inside. Every mission that managed it, Dawn at Vesta and Ceres, OSIRIS-REx at Bennu, Hayabusa 2 at Ryugu, returned knowledge no flyby ever could. Nuclear propulsion may someday make that arrival cheaper and faster. Until it does, the pace will keep being set by the same rule it always has. The belt was never the barrier. Learning to slow down was. And we are only just getting good at it.